All right, today we're going to talk about level curves and level sets, which is kind of like we kind of started talking about that, but let's formalize it a little bit better and do some examples that maybe may or may not be easy. I don't know. So notice that I have here level curvaces / surfaces, and sometimes people refer to this as just level sets for a graphical representation of a function of more than one variable. So let's take a look at, we took a look at one already in detail. Let's take a look at a simpler one. Let's start with z is equal to x squared plus 2y squared, or something like that. Let's start off with this and say this is a surface, and hopefully by looking at this you can see that the x is squared, the y is squared, the z is on the other side. So hopefully you can think of this as a paraboloid. Now since there's a plus in between them, it's going to be more of an elliptical paraboloid instead of a hyperbolic paraboloid. And we'll see that it is in the shape of a paraboloid, and we'll see why it's called an elliptical paraboloid versus the other one that we saw yesterday, which is a hyperbolic paraboloid. And so to get level curves, they call them, or level sets, level sets are obtained by letting your output variable z equal to some different values, different constants, and trying to see what the shape of the graph might look like. So what we're going to do is we're going to let z equal to a bunch of numbers. Let's say usually 0 is a good place to start. Z is equal to 0. We have 0 is equal to x squared plus 2y squared. And so I'm going to get myself ready here with a graph. This first one is only, what is this? It's nothing but a point. It's just a point. So z is equal to 0. All we have is a point. And I'll leave it like this for now, and I'll try to find a nice way to label it a little bit later on. Z is equal to 1. We have 1 is equal to x squared plus 2y squared. So this is where you have to start being able to look at something like this and then be able to determine what kind of a graph it is, and whether you need to shuffle things around to make it look like something that you're familiar with, or you can just eyeball it and say, oh, hey, that's an ellipse. Either way would be good. But if you want to do some work, a little bit of legwork here, it looks like this is already equal to 1, which is good news. I probably just want to make this into a y squared over something because I'm more familiar with it in those terms. So x squared over 1 squared plus y squared over, now the 2 on top goes down to the bottom as a 1/2. And if I really want to be formal about it, I'll write it as 1 over square root of 2 quantity squared. So, but the point is that this y value is going to be less than this 1. The b value, if you remember the equation of an ellipse, it's x squared over a squared plus y squared over b squared is equal to 1. So the x's look like they were going to cross the x-axis at 1, and then the y will cross the y-axis at 1 over square root of 2, which is, I don't know, 0.7-ish or something like that, less than 1. So it looks like our ellipse will be elongated along the x. And then if we follow this with more values of z, going through the same process so that you can rewrite it, I would divide both sides by 2. So x squared is equal to the square root of 2 quantity squared, so that's the 2 down there. The 2's would cancel on this one, so that would just leave the y squared over 1 squared is equal to 1. So here square root of 2 is bigger than 1, so it'll be bigger than 1 over here, and then it'll be 1 on the y-axis. So we'll see that it's just going to be concentric ellipsis growing outward. Now the other thing to check for is I started with 0 and then I started putting 1, 2, and etc. So it's always good to go down to see if whatever the surface looks like, if you cut it with a plane that's below the x-axis, what the shape is going to look like. And if we do that, I put negative 1 is equal to x squared plus 2y squared, we'll see that the left-hand side is negative, but the right-hand side is always positive. And so this will never happen. And that means that this graph will not intersect the plane z is equal to negative 1. So now that we have this, we can try to imagine how this would look like in 3 dimensions. And one way to do that is that if you imagine your x and your y, and so this part is not that big of a deal anymore, but if you can try to imagine how this might look like, see if I can do some magic here. So this is how it would look like tilted a little bit so you can see, and now we just move these ellipses up higher so that you can kind of see the shape happen, and then it'll end up looking like kind of like a bowl. That would make your 3-dimensional elliptical paraboloid. All right, so this part is not that big of a deal. Let's not worry about this. But if you can visualize it, that's great. But that's not that important in terms of trying to identify your level sets. Your level sets are going to be these things. And since they are 2-dimensional curves, we just usually would call them level curves. And then we can label them now. We can label it the way we saw the contour curves, like contour maps labeled. We could just put 0 here and a 1 here, or and then a 2 here, or something like that. You can label it like that. Or you can be more specific, say z is equal to 1, z is equal to 2, etc. All right? So this helps us to visualize things going from 2 dimensions to 3 dimensions. And to get back to the notation that I introduced last time, this can be seen as a function f going from a two-dimensional domain. So you got the x, y as your points that's going into the function, and then you got your z, scalar, as your output going out of the function. So the visual representation is that you would visualize the R2, the x and y, as flat on the xy plane. And then the third dimension that we can still visualize is your output. So we kind of saw a picture of that being drawn out last time. All right, good? So you'll probably get things that might be slightly more complicated than just ellipses, so that's why we studied the conic section, so that you can be prepared if you see lines, or if you see hyperbolas, or if you can see circles, whatever it is, parabolas. It would be good to be able to identify that and just off the top of your head say, okay, that's what this is. Draw it out. All right, now let's take this a step up. another example of level sets. And this time, we're going to take a look at a function that takes three-dimensional points and send them to a one-dimensional output. And I think I remember the notation that we use is W for your output. And your input is three-dimensional, so we tend to just call it X, Y, Z. And for this, I'm going to copy an example that they have in some notes here. X squared plus y squared minus z squared. Now let's try to imagine how this thing might look like by looking at the level sets. So the level sets, again, are the relation between your input variables, your x, y, and z in this case, based on setting your output variable as a constant. So we're going to take a look at a level set when w is equal to 0 to begin with. And so we'll set this whole thing equal to 0, get x squared plus y squared minus z squared is equal to 0. And now what we have to do, our task is to look at this and say, oh, that is a shape of something. So let's see. I don't think I could do much more here. I maybe bring the z over to the other side. I don't know if that'll be much help. But my hope is that we see these shapes, we see these equations enough times that one of these days you'll just look at that and say, oh, that's a cone. Of course it's a cone. This is a cone. Okay? I don't know what else to say. This is a cone. Aside from, look at your notes. So one time I stole a big sheet of notes from one of the YouTube videos that we haven't watched YouTube videos in a long time before class starts, but this one video had a sheet that had all kinds of stuff in it that looked really interesting. Now I said it wasn't going to be on a test, so all that stuff probably kind of filtered away and left. But it's there somewhere. It's in one of the notes. I'm not going to look for it right now. But you have to look at this and say this is a cone. All right, this is a cone that opens up and down. It's z squared is equal to x squared plus y squared, so it actually is capturing both cones, the top and the bottom, and z is the one on the other side, so it's opening up along the z-axis. So if I was to visualize this now, this is just a level set. So I would look at this in 3 dimensions and say, okay, I have this first cone over here, the cone that opens up and down along the z. Maybe it should be wider than that, but let's just draw it like this and say, okay, this is one level set. This is a level set where w is equal to 0. So notice now the difference is that last time our level sets were in 2 dimensions, and we can draw that easily. Now our level sets will be in 3 dimensions, and so our level sets would actually be surfaces. So in fact, sometimes they call it level surfaces in 3D because your outputs, you're generating level sets. So that's one of them. Let's let w equal to 1 this time. So 1 is equal to x squared plus y squared minus z squared. And say, oh, okay, now there's a 1 on the other side. So it's not just 0 on the other side. It wouldn't make much sense for me to bring the z over to the other side. But if you look at this, maybe if you look at it from this point of view, I don't know if this will help any, but you have to look at that and say, oh, okay, that is a hyperboloid. Right? Yeah, sure. It's a hyperboloid. Now, is it a hyperboloid of 1 sheet or 2 sheets? So I have two positives here and one negative, two of the same signs, and one, z is the one with the opposite sign. So what if I let z equal to 0 in my head? If I let z is equal to 0 in my head, I would see that this, it'd be x squared plus y squared is equal to 1. So z is equal to 0, the xy plane, it looks like it's just a circle, right? So this must be a hyperboloid of one sheet that's connecting everything. Okay? So that's another level. We'll call this w is equal to 1. We could do w is equal to 2. And we'll essentially get the same thing. X squared plus y squared minus z squared is equal to 2. Now, if you want to make it look like a hyperboloid and divide everything by 2, then it'll still be a hyperboloid. And, in fact, it'll still be a hyperboloid of 2 sheets. So it just have a wider base in the bottom, that's all. All right, so we get some pictures here that may or may not make sense. But before we put it together, remember I started with 0 and I went positive. So what if we go negative and see what happens when we go on the other side? Let's try w is equal to -1. So I have x squared plus y squared minus z squared is equal to -1. If I really want to make it look like the equation of the hyperboloid, because I'm looking at this and say, hey, that's a hyperboloid. If I want to make it look like an equation of a hyperboloid, maybe I'll take the -1 out and multiply everything by negative or something like that. And I don't know if this is going to be more confusing. But I still have two of the signs are negative, and then one sign is positive. Two of the signs are the same, one is different. So it's still going to be opening up somehow along the z-axis. But this time I have this situation, and if I know it's opening up along the z-axis and say, okay, what if I let z is equal to 0 and see what happens? And so off to the side here I say, what if I let z equal to 0? Then I would get 0 minus x squared minus y squared is equal to +1. And you know that this is never going to happen, because you here on the left-hand side you have a number. Regardless of what number you put in for x and y, it's always going to be negative. And then the right-hand side is +1. So we know that it's not going to hit the xy plane. Which means, and I also know that this is a hyperboloid, so which means this is going to be a hyperboloid of 2 sheets. And it's opening up along z. So inside of that cone, I have this hyperboloid of 2 sheets. And I would probably label this as my level set for w is equal to -1. I missed this one. This is w is equal to 2. And then this is the other part of w is equal to -1. Okay? So essentially you have these family of surfaces, kind of like this family of ellipses. I have a family of surfaces that is made of hyperboloids of 2 sheets, hyperboloids of 1 sheet, and a cone. Yeah.
Would it also be like shorter, like w equals 2?
I'm drawing it shorter so we can see the inside. Yeah, but no, these are all infinitely going on forever. Anything else? So now here's the next step, which we're not going to take. Before we go into the next step that we're not going to take, let's look at our first example where we have curves in 2 dimensions, and then if you have a strong visual sense, a spatial sense, they call it. If you have a strong spatial sense, you can take these curves with these levels and be able to visualize a three-dimensional surface out of that. And this is your paraboloid. Let me actually draw this a little bit better. So the visual that you would get out of this is a paraboloid with elliptical cross sections. Right? You see how these cross sections of ellipses get extended up into this three-dimensional surface. And so there's going to be some there's some 2 to 3-dimensional drawings that we can visualize. Some will be a little bit more difficult, but it can be done somehow. It can be visualized somehow. Now, back to our step that we're not going to take. In 3 dimensions, or when your domain is in 3 dimensions, and then you have a 4th dimension as an output, now this is something that you can't visualize as a whole. The best you can do is but best you can do is picture what the level sets would look like. To take this jump from 3 dimensions to 4 dimensions is, well, since we live in 3D, it's basically impossible unless you put some 3-dimensional or 4-dimensional glasses on. There's no such thing as 4-dimensional glasses. Or some mental help to help you reach that 4 dimensions. Chemical help, maybe. So back in college, my 4D glasses were just, stuff. Helps you visualize in 4 dimensions. Since you can't do it in real life, you have to go in an alternative world. Anyways. Good old days. So 4 dimensions is not something that we can visualize. We can, at best, imagine it, and imagine it using level sets in 3 dimensions. And then whatever happens in 4 dimensions is going to happen. But at least we can visualize the level sets, the level surfaces, because it's still 3D. All right. Okay. Now let's move on and talk about limits and continuity. I've done a couple of examples of this. By the way, this is a really crappy picture. I know I'm not trying very hard. I should try to be more artistic. But if you can, practice drawing these 3-dimensional surfaces. It'll be good for us in the long run. Good for you in the long run. All right, now let's talk about limits and continuity. And to begin, let's go back to, I guess, calculus, pre-calculus, I don't know, one of those places where we did limits and continuity first. And back in one variable land, the way we loosely defined limits existing and something being continuous is that limits have to satisfy 3 things. One, the point has to be defined. So limit at x equals a has to satisfy 3 things. First, f of a has to be defined. And second, the limit as x approaches a of f of x has to exist. And then the third, the limit as x approaches a of f of x, which we said existed, has to actually be equal to f of a, which we said was defined. So these things have to happen for the limit to exist. Now, what are some reasons why the limit might not exist? Don't exist. In the following examples, so first of all, it actually has to be defined at that point. Come on, purple. Oh well. So as an example, maybe y equals 1 over x, or y equals x squared minus 1 over x minus 1. Here are a couple of examples where the first one is not satisfied, a is not defined. So here at 0, a equals 0. The limit doesn't exist there, because if you put 0 in the denominator, it'll... Oh, I should put limits and continuity here, sorry. Sorry about that. Continuous. These three things have to be satisfied for it to be continuous. Sorry. I'm going to erase this and say not continuous here. So these are a couple of examples where f of a is not defined, and if it's not defined, then the limit doesn't exist. This is a little bit more interesting, though. The first one, you have 0 in the denominator, that's fine, it goes away, and the graph clearly shows it goes to negative and positive infinity, so it's not defined there. This one's a little bit more interesting. At 1, I don't know if you guys can imagine how this graph looks like, but this graph is really just a line if you were to graph it in your graphing calculators. It looks like a line, and at first glance, it looked like it would be continuous there. But there's something happening, right? There's a hole at 1. So there's actually a hole there, and it's not defined there because if you put 1 into this function, you're going to get 0 over 0. Well, really, the 0 in the denominator kind of eliminates that as being part of the domain. So this function is not defined at x is equal to 1. So we have a hole. It's not continuous there. Notice that the limit does exist, though, right? So the limit still does exist, so that's something to look at. So there's going to be other functions where it might be defined, and sometimes the function could be defined piecewise. So it'll be 1 over x as long as x does not equal to 0, for example, and we'll define it to be 0 if x does equal to 0. So it'll be like the same function over here, except you add on a point, 0, when x is equal to 0. So now it's defined at 0, but does the limit exist? In this example, the limit doesn't exist because if you go from one side, it goes up to positive infinity. If you go from the other side, it goes down to negative infinity. So the limit doesn't exist here. So now it's defined. F of 0 is defined, but limit as x approaches 0 of f of x, it still doesn't exist. DNE does not exist. Okay? Now, speaking of piecewise functions, we can have other piecewise functions. Here's a simple piecewise function. F of x is equal to 0 if x is less than 0, and it's equal to 1 if x is bigger than or equal to 0. This is a popular function that's studied in differential equations called the Heaviside Function. And this helps define a bunch of other types of scenarios where you're trying to model something and it's going to be off for a certain amount of time, and then you turn it on. So this is what happens. It's off, and then it goes on. So this is another example where your function is defined at 0. It's 0 until you get to 0 with an open circle, and then you have a closed circle at 1, and then going on to the rest of there. So the function is still defined at 0, but the limit doesn't exist because you're coming from one side, it's one thing. You're coming from the other side, it's another thing. So here, the limit DNE does not exist because two-sided limits don't equal each other. Two-sided limits are not the same. Or not equal. So here are a couple more scenarios where the function might not be continuous because the limit doesn't exist. And then there's some other weird functions where the limit does exist and it's defined, but they're not equal. Usually a piecewise function where you just put the dot in the wrong place and then they all of a sudden become equal. All right. So that's the idea behind limits and continuity. And in terms of studying these functions of several variables that we have, we're going to look at limits a little bit more closely and focus on that a little bit. Okay? All right. So now I want to put the title just limits. So in the previous page, we took a look at some examples where limits might not exist, and usually we focus on two-sided limits. Not usually, but one scenario is that when we focus on two-sided limits, we got A coming from one side, A coming, or X coming from one side of A, and then X coming from the other side of A. So the limits have to agree coming from both sides. Are you guys familiar with these types of problems when we do limits? Okay. So now I want to jump up, well, before I jump up to functions of two variables, I want to focus on this number line. This is your x, this is your input. So these are your f functions going from R to R. And your x is your input variable, your domain. Your domain is one-dimensional. It's a one-dimensional thing, which means it's a straight line or it's a line. And if you want to reach a point on that line, you really have two directions to go. Okay, so that's where the two-sided limit comes from. Let's take this with functions of two variables. And we got the idea already of how these functions of two variables work. Your input is a two-dimensional point. That's your two-variable function. And your output is one-dimensional, and that usually, from a graphical perspective, gives us the height. And it could be height going up or going down, whether it's positive or negative, but we're looking at the input being two-dimensional and then the output being one-dimensional. So your input is your domain. Your domain is a two-dimensional thing, and then your output is a one-dimensional thing. So now the idea is that if you have a surface, this is my surface, let's call it z is equal to f of xy. By the way, this is going to be my favorite surface from now on. Every time I need to draw a surface, I'll draw this. Kind of like back in calculus, whenever I say I need a function y is equal to f of x, and then I would draw this, whatever that is. Right? So that's a function in y is equal to f of x. This is going to be my surface. Z is equal to f of xy. So let's put it in the x, y, z space. So it's just the surface that's kind of floating above the xy space. And then say this is the shadow that you have on the xy plane. So when we're talking about limits approaching a particular point, when I say point in the domain, I mean a two-dimensional point here. We use AB or X naught, Y naught. Let's use AB. Did something happen? So AB is a specific point on my domain. It's a two-dimensional point. And then so I'm curious to see what happens on the surface itself. Okay, think about that as this thing, A, and you're just looking at a curve. So on the curve, you're just moving along in a one-dimensional axis. So this, your only direction is going from, I guess, left to right or right to left, one-dimensionally. And you're riding along this curve. Now, here, you're looking at this point on the xy plane, and you're seeing what is going on that surface near that point. Is my surface going to be nice and smooth, or is there going to be some weird things happening in that surface? Is there going to be a hole in that surface? Or are there going to be cliffs there? So we'll see that there's all kinds of weird things that could happen that's going to be physically hard to represent. And I can't think about whether to call it a cliff or a gorge or something. There's going to be some weird things happening. If it's a nice, smooth surface, which is mostly what we're going to be doing anyways, then that's not going to be an issue. But we're studying limits and stuff, so when we study limits, we look at the odd things that might happen to limits. So the question is, what's happening near there? Now, this circle that I drew up on the surface has a little bit of a shadow of the circle on the xy plane. So think about this as you on the mountain, and then think about the xy plane as your map. It's a two-dimensional thing, your map, right? And so that gives you some sort of direction and gives you a point of reference where you are in 2 dimensions, but you're really up in 3D, up with some height happening. So the question is, what's happening there? Now there's, like I said, in the simple case where we're in pre-calculus functions, you go from one side, you go from the other side, and then you're going to reach your point, right? You only have two ways to go. So that's a two-sided limit business. Over here, if you're looking at that map and you're looking at this point, you want to get to that point, there's a few ways to go there too, right? You can go north, south, east, west to get to that point. You can go southeast, northeast at some sort of diagonal or some other angle in the diagonal. Or you can approach it, you know, at some sort of path. I just ruined that picture, didn't I? Let's take a look at that picture from a map point of view. So what was I saying again? You can approach this point horizontally, vertically, diagonally, at some slope in the diagonal. You can even approach this point from a curve path. You can even approach this point from a spiral path. The idea is that, what am I trying to say here? Back in calculus, pre-calculus, there was two ways to approach the path, from the left and from the right. Here, there are many more. And if you were to count them, you would say infinite. There are an infinite number of ways to get to that point. Okay? And the idea is, you know, for this, there's two ways. If you go one way and you go the other way, and then you see that those two don't meet, then you can say, oh, it's not, the limit doesn't exist. Okay? Over here, you go one way, you go the other way, you go another way, you go another way, and they don't meet. You can't say that the limit doesn't exist because you've only tried four ways. Then you go diagonally and through some curves, and you can go 500 different ways to reach the same path, and you get the same height. You're still not sure if it's correct. And so the point is that we can check for paths to get to a particular point on your mountain in 3D. And if two of them give you two different heights, then you can say that this is not continuous. If 15 of them give you the same thing, then you can't conclude anything because you're still not sure if continuous. You're still not sure if you missed one path that will give you a different point. And so to prove that something is continuous, or to prove that the limit does exist, is a lot more difficult in this higher dimension sense. So you would need to use epsilon deltas. Do you guys remember epsilon deltas at all? It's because they probably didn't teach you. And when I teach Calc 1, I talk about it, mention it, and maybe give a small quiz question on it. But it's usually not covered in typical calculus class. And so that's because it's a higher level of mathematical thinking that we don't need to worry too much about. Unless you're a math major, then you'll be living in epsilon delta world when you get to one of your classes. But we won't do that. So so this is a strange phenomenon. The best thing to do is to take a look at an example. And then I said I wasn't going to do any graphs, but I'll probably want to do a graph of an example and try to see if we can visualize it in 3 dimensions and how weird it's going to look like. All right, so let's do an example. And remember, these types of examples are the ones where limit does not exist, and that's the more interesting examples. And it's, you know, and realistically in real life situations, these things are hardly ever going to come up. but in math it's fun to study. So let's take a look at a function z, or you can say f of xy is equal to x squared minus y squared in the numerator and x squared plus y squared in the denominator. And the point in question that we're concerned about is 0, 0. Because clearly it doesn't, the point doesn't exist there because you have 0 over 0. Now the question is that, does it all get flattened out nicely for us so that we can still look at it as a surface and climb it and stuff like that, or does it get really weird? There's all kinds of weird traps and caverns and scorpions. So, so why don't we just come out and say, show that the limit doesn't exist here. And if I tell you that the limit doesn't exist here, your task will be to find two paths where the limits are different. So you're probably saying paths. What are paths? What do you mean paths? So remember that we're going to look at this from a two-dimensional point of view, and if you can imagine the third dimension, then that's fine. But really, your focus is on two-dimensional point of view, and you're going to take a look at equations that you've seen before, like x is equal to 0, y is equal to 0, those types of equations, right? So let's take a look at paths. And the path, we can look, we could parameterize it and do all that fancy stuff, but we don't have to be all that fancy. Let's take a look at a couple of paths here at the same time. And the arrows that I just drew here are reaching that point that I'm interested in, 0, 0, but it's reaching it when y is equal to 0. So let's call this path 1. When y is equal to 0. So we have that path, and all you really have to do is look at this equation and set y equal to 0. Can you guys see that? Is that too light? Maybe we can darken it a little bit. That's the same one. I don't know. All right. So what we're going to do is that when y is equal to 0, y is already 0. So I want the limit as something, and then y is equal to 0. So I have x squared minus 0 squared, x squared plus 0 squared. And you notice when y is equal to 0, your y variable disappeared, and you only have an x variable left. So I want to see what happens when x approaches 0. And then from there, I can go from left or right side, but I think we're going to come out with the same thing. So this is, we'll just say this is a general limit. Now I've reduced my two-dimensional problem into a one-dimensional problem limit, where I'm just looking at the x instead of the xy. And if we go ahead and do a little bit of work on this, you got x squared over x squared, and before you even take the limit, this is already equal to 1. So that's just going to have to equal to 1. Okay? So it looks like we have a limit of 1. If you were looking at your map and you're following this path and you're going along the north-south no, sorry, east-west of that point, you're going to get to that point in the mountain at a height of 1. Okay? All right. Now let's take another path. Our second path is the y-axis, and sometimes the y-axis can be referred to as x is equal to 0. So let's work with that. Limit as, now I want to put x is equal to 0. And if I put x is equal to 0, the only variable I have left is y. So that's just y. So this is a y limit going to 0. Okay, so let's work that out. Y approaches 0 of, this is minus y squared on top, positive y squared in the bottom. And again, before you take the limit, this is already a constant, and it's negative 1. So unfortunately, this is not equal. So imagine there's this mountain. You and your friend are in this mountain. You decide to take path 1, going and say, hey, I'll meet you at 0, 0. Right? You take path 1, and you're going to be 100 feet up in the air, positive. And your friend takes path 2, looking at the map and say, we'll meet at 0, 0. So your friend takes path 2, and then your friend ends up being 100 feet down below. So clearly, those two limits are not the same, right? So we have to say, since these two are not the same, since two paths give you different results, we have to conclude that the limit doesn't exist. So this graph has a limit that does not exist at 0, 0. Okay? So we did this work analytically. Can you imagine what the shape of this thing is? Imagine that you're going one way and you're up one level up and your friend's going the other way and they're down one level down. Can you imagine how this graph would look like? It'd be weird, right? So this is an example of a graph that is not continuous at 0, 0 because this weird thing happens to it. So let's see what this graphing calculator program can get us out of this graph. So this is an x squared minus y squared in the numerator, and then x squared plus y squared in the denominator. So remember that these graphing programs, regardless of how rigorous or how advanced they are, they're still might not give you the whole picture. And here you see that little V opening over there, either above or below, that actually technically is connected. Except the graphing program is not allowing us to see that because the graphing program does approximations and things like that. So it's not 100% accurate. What's happening here is that if you look at running along the x-axis like we were talking about, going along the x-axis, you see that you're up above, and then your friend going along the y-axis is down below. Maybe we can exaggerate this a little bit. Maybe take a picture of it. That's a nice view. So our path 1 versus our path 2 in 3 dimensions now clearly shows us the 2 different heights that we would run into. And so at 0, 0, we can imagine this thing here, a little crevice or something that where something weird happens to the surface, and now the thing doesn't exist. Okay, I think the general rule of thumb, you know, in 2 dimensions in calculus, they say a graph is continuous if you're able to draw your pencil. Using your pencil, draw the graph without lifting it up the paper and then coming back down. So similarly, we can think about surfaces as being continuous or being nice. If you take one piece of surface, like a piece of rubber sheet or something like that, you can twist it and pull it and shape it to any way you want. But when you start tearing it up, you know, when you start ripping it and heating it up so that things get stuck together, imagine doing this to a piece of rubber sheet and making a shape out of this. You're essentially going to destroy that rubber sheet, and so it's not going to be nice and continuous anymore. So that's kind of like what's happening. All right, there's one more cool example. This is this is your basic first example of these things, because you're looking at paths going along the axis. So let me put up a quick example. I don't know how much of this we'll do, but we'll put up another quick example of another surface to check if it's continuous or if it has a limit. Yep. Let me say f of x, y. And here they actually define it as a piecewise function with the hopes of it being continuous. We have a sine x squared plus y squared. Is this the one I want? I'm sorry. No. This is another good example, but I don't want this one. My eraser. Oh, that's not my eraser. All right, something's happening with my program. xy squared over x squared plus y to the 4th, as long as xy is not equal to 0. And then 0 if xy is equal to 0. So we want to see if we can find 2 paths that give us different results. And let's get our visual here. And let's take a look at our 2 basic paths that we normally go with. Either x is equal to 0 or y is equal to 0. So path 1, y is equal to 0. And when y is equal to 0, we're taking a look at the limit of x times 0 squared over x squared plus 0 to the 4th. And so if I put y equals 0, then clearly my my y's are gone, so I really just have one variable x, and I want x to approach 0. Well, if you multiply the numerator, it's going to be 0 on top. And again, before you even take the limit, this is already going to be equal to 0. So similarly with path 2, you got x is equal to 0, so we have 0 times y squared, 0 squared plus y to the 4th. Y approaches 0. So limit as y approaches 0, and again, this is going to be 0 in the numerator, so that doesn't do us much. So let's try another path. So let's get a path that maybe at a diagonal. So let's call this path 3. And this looks like the y equals the x line. So we can approach this from one of two ways. We can replace x with y or replace y with x. In any case, I would have x cubed on top, right? Let me just say x times replace y with x. So that's x squared, x times x squared. Limit as x approaches 0, and then the denominator is x squared plus y squared, or y to the 4th, sorry. But I'm replacing x with y. Let's see how this is all going to work out. This is limit as x approaches 0 of x cubed over x squared plus x to the 4th. Let's see. You can factor out an x squared from the denominator. 1 plus x squared. So this is your denominator factored, and we can cancel one of the x's on top. Or two of the x's on top, so we would have an x left on top and then a 1 plus x squared in the bottom. Did I do that right? Took out an x squared. So now if I let x go to 0, I'm going to get 0 on top and 1 in the bottom. That's equal to 0. So it looks like with the three paths that I'm taking, it's all going to be 0. In fact, for a lot of paths that you take, we're going to get the 0. So we want to look for that one path that's going to give us something different. And the one path, I think, the one path that's going to give us something different is an x equal to y squared. So we're out of time, so you figure this out. If you put y is equal to x or x is equal to y squared, then you'll see that your result is going to be something else, not 0, and therefore would give you a different limit, and so the limit won't exist. Okay? So I'll put dot, 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 not equal to 0, so limit does not exist. All right? All right, go with that and see what happens. Next time should be able to talk about partial derivatives.